Right, let's talk about something a bit heavy. There's a metal out there, a substance so potent it's almost mythical. It's a forbidden metal, born not in the fiery heart of a star, but in the quiet of a human laboratory. This metal is plutonium. It's a heavy, silvery white element that tarnishes to a dull gray when it meets the air, but its appearance hides its true nature. It is a substance that holds immense power, the kind of power that can either light up a city or wipe it off the map entirely. It is one of the most complex and fascinating elements known to science, and its story is tangled up with the most significant moments of the 20th century, shaping our world in ways we are still grappling with today. For most of human history, it was completely unknown, as it barely exists in nature. You won't find a miner digging up plutonium ore from a deep cavern. Instead, its existence began as a theory, a missing piece in the grand puzzle of the periodic table. Its discovery was a landmark achievement, a testament to human curiosity and our drive to understand the very building blocks of the universe. This discovery, however, opened a Pandora's box of possibilities, both brilliant and terrifying. It pushed science into a new age, the atomic age, and with it came responsibilities and dangers on a scale never before imagined by humankind. The discovery happened in the United States, on the cusp of its entry into the Second World War. On a cold December night in 1940, at the University of California, Berkeley, a team of dedicated scientists finally created and identified this new, man-made element. The world was on the brink of a global conflict of unprecedented scale, and this quiet scientific breakthrough would soon roar onto the world stage. The men who found it were Glenn T. Seaborg, Edwin M. McMillan, Joseph W. Kennedy, and Arthur C. Wall. They were pioneers, stepping into uncharted territory, and they had no way of knowing their discovery would redefine the concepts of power, warfare, and even peace itself for generations to come. Their work was kept secret for a good while, and for good reason. As the properties of this strange new metal were uncovered, its potential for creating a weapon of unimaginable destructive force became chillingly clear. The creation of plutonium wasn't an accident. It was the result of a deliberate and brilliant experiment. It all took place within the walls of the Berkeley Radiation Laboratory, using a machine that was at the cutting edge of physics at the time. This machine was a particle accelerator, specifically a 60-inch cyclotron. Think of it as a massive, powerful slingshot for subatomic particles. The team of scientists, led by the visionary Glenn Seaborg, had a clear goal. They wanted to bombard a known element, uranium, with particles to see if they could force it to change, to transmute into something entirely new. It was a modern form of alchemy, but this time it was based on the hard science of the atomic nucleus. The process they used was incredibly precise. They took a sample of uranium oxide and placed it in the path of a beam of deuterons. A deuteron is the nucleus of a heavy hydrogen atom, made of one proton and one neutron. The cyclotron accelerated these deuterons to incredibly high speeds, giving them enough energy to slam into the uranium atoms and penetrate their nuclei. This collision was the key moment. It knocked a piece of the uranium atom out and created a new, heavier element. This first new element was unstable. They named it Neptunium-238. But the scientists suspected that this was just a stepping stone to something else, something more stable and more interesting. The initial discovery was just the beginning of a monumental effort. The isotope they made, Plutonium-238, was not ideal for a weapon. The real prize was another isotope, Plutonium-239. This form was predicted to be fissile, meaning its nucleus could be split easily, releasing a huge amount of energy. To make this, they realized they didn't need a cyclotron. They could use a nuclear reactor. Inside a reactor, uranium atoms are constantly splitting and releasing a blizzard of neutrons. When a uranium-238 atom, the most common type of uranium, absorbs one of these neutrons, it eventually decays into plutonium-239. This discovery shifted the focus from small-scale lab work to a massive industrial undertaking, a secret race to produce this new material in bulk. First done at scale at the Hanford site in Washington state during W-Dows, in giant remote-controlled canyons. The chemical separation work was, and still is, incredibly hazardous. Every step must be done by remote control, workers shielded by thick concrete walls, workers viewing through lead-lined glass. The result, a small quantity of pure plutonium metal ready to be used. The journey from a uranium fuel rod to a purified sphere is a testament to scientific ingenuity, but it also leaves a legacy of dangerous radioactive waste that must be managed for thousands of years. Plutonium is a material of profound duality. Its properties make it exceptionally useful for a few very specific high-stakes applications. You can neatly divide its main uses into two camps, creating destruction enabling creation. On one hand, it is one of the primary materials used to build nuclear weapons, the most destructive devices ever invented by humanity. On the other hand, a different form of the same element is an irreplaceable power source that has allowed us to explore the darkest, most distant corners of our solar system. This stark contrast is at the core of plutonium's identity. It is a tool of immense power, and like any such tool, its impact depends entirely on the hands that wield it. The most famous, or perhaps infamous, use of plutonium is in nuclear weapons. Specifically, the isotope plutonium-239 has the perfect properties for a bomb. It is fissile, meaning its atoms can be split by neutrons to create a powerful chain reaction. A sphere of plutonium-239, about the size of a grapefruit, contains enough destructive energy to level an entire city. But there is another side to plutonium. The isotope plutonium-238 has a completely different set of talents. It is not fissile like its cousin, so you can't make a bomb out of it. Instead, it is intensely radioactive in a very useful way. The story of plutonium is inseparable from the story of the atomic bomb. When scientists realized plutonium-239 could sustain a rapid chain reaction, it became the focus of the Manhattan Project, America's secret wartime effort to build a nuclear weapon. One team worked on a uranium bomb. Another at Los Alamos was tasked with a weapon using plutonium. Building a plutonium bomb was much trickier than a uranium one. Reactor-produced plutonium contained a small amount of plutonium-240, which made it too unstable for a simple gun-type design. Los Alamos scientists under J. Robert Oppenheimer developed a revolutionary solution, the implosion device. The idea: start with a hollow sphere of plutonium that was subcritical. It couldn't sustain a chain reaction on its own. Then crush it violently and symmetrically into a smaller, denser, supercritical mass. They surrounded the sphere with a carefully shaped arrangement of high explosive lenses designed to detonate with microsecond precision. The detonation sent an inward-moving shockwave, squeezing the plutonium to a fraction of its original size. That sudden compression triggered the runaway nuclear chain reaction. The design was first tested on July 16, 1945, at the Trinity test site in New Mexico. Trinity was a terrifying success. It vaporized the steel tower and produced a mushroom cloud miles high, a flash brighter than the midday sun. Weeks later, on August 9, 1945, a Fat Man bomb based on the same implosion design was dropped on Nagasaki. The explosion and aftermath caused immense devastation and helped end World War II. Since then, plutonium has remained central to nuclear weapons strategy. The implosion design became the basis for the primary stage of thermonuclear weapons. Plutonium's compact energy density makes it ideal for powerful warheads. Nuclear states maintain plutonium stockpiles and handling facilities. Production, security, and dismantlement of plutonium remain major international political and security issues. Ever since, plutonium has remained a key component in the nuclear arsenals of several nations, a silent guarantor of a tense and fragile global peace, a concept known as nuclear deterrence. While one form of plutonium brings the threat of destruction, another form, plutonium-238, has been absolutely essential for some of humanity's greatest voyages of discovery. Space is a cold, dark, and unforgiving place, especially once you travel beyond the orbit of Mars. Out there, the sun is just a distant, bright star, and solar panels become increasingly large and ineffective. For missions to the outer planets and beyond, scientists needed a power source that was small, light, reliable, and could last for decades without any maintenance. Plutonium-238, packaged inside a radioisotope thermoelectric generator, was the perfect solution. An RTG is, a masterpiece of simple, robust engineering. Inside is a ceramic pellet of plutonium-238 oxide. As the atoms decay, they heat thermocouples to generate electricity for many years. The twin Voyager 1 probe and the twin Voyager 2 probe, launched in 1977, are still operating today. Cassini at Saturn, New Horizons at Pluto, and the Curiosity and Perseverance rovers on Mars all relied on RTGs. There is no getting around it. Plutonium is one of the most dangerous materials on Earth. Its danger comes from several different properties. First and foremost, it is highly radioactive. Plutonium primarily emits alpha particles. Alpha particles are big and heavy on a subatomic scale, and they can't travel very far. They are easily stopped by a sheet of paper or even the outer layer of your skin. A piece of plutonium sitting on a table is not an immediate external threat. The real danger comes if it gets inside your body. If you inhale even a tiny speck of plutonium dust, alpha particles are released into your tissue. If you swallow even a tiny speck, the same internal release occurs. Once inside, plutonium becomes a serious health hazard. Inhaled particles can lodge in the lungs and irradiate cells for years, raising lung cancer risk. If it enters the bloodstream, the body treats it like iron. It then accumulates in the liver and on bone surfaces. That constant alpha radiation can lead to liver cancer or bone sarcoma. Because it's so toxic when inhaled, plutonium is often called one of the most toxic substances known. Another major challenge is its incredible longevity. Weapons-grade plutonium-239 has a half-life of about 20,100 years. In 20,100 years, half will still be there, still radioactive. It takes 10 half-lives, nearly 250,000 years, to reach relatively safe levels. That timescale is a monumental waste management challenge. Because plutonium is the key ingredient for a nuclear bomb, keeping it out of the wrong hands is one of the most serious global security challenges. This is the problem of nuclear proliferation. The fear is that if a terrorist group or a rogue state were to acquire enough plutonium, an amount known as a significant quantity, about 8 kilograms, they could build a crude but devastating nuclear weapon. Therefore, every gram of plutonium, whether in a weapon, in a reactor, or as waste, must be meticulously accounted for and secured. This task involves international treaties, inspections, advanced security technologies. The main international body responsible is the International Atomic Energy Agency, the world's nuclear watchdog. Under the Nuclear Non-Proliferation Treaty, countries without nuclear weapons agree not to acquire them and allow the IAEA to inspect facilities. Inspections verify material is for peaceful use, like generating electricity, and not diverted to weapons. Inspectors use seals, cameras, measurement devices to keep track and make sure everything adds up. Facilities are among the most heavily guarded places on Earth, protected by high fences, armed guards, motion sensors, robust vaults. Transport uses heavy crash-tested casks engineered to survive extreme crashes, fires, explosions. It's defense in depth. As we look to the future, plutonium will continue to play a complex and challenging role. Its story is far from over. For the foreseeable future, its presence will be defined by three main areas: dealing with the legacy of the past, powering new ventures in science, and debating its role in our energy future. The massive Cold War production left behind contaminated sites and radioactive waste. Hanford site in the US, Mayak facility in Russia, are undergoing decades-long, multi-billion-dollar cleanup efforts. Scientists and engineers are developing new technologies to safely retrieve, treat, and store plutonium waste, likely in deep geological repositories. At the same time, plutonium-238 will remain our go-to power source for exploring the outer solar system. With new production underway, NASA and other agencies can plan ambitious missions to icy moons and distant planets. The debate over plutonium in future energy systems continues. Fast reactors and molten salt concepts could burn stockpiles and generate low-carbon power, potentially closing the fuel cycle. But cost, safety, and proliferation concerns remain. Building a future that uses plutonium safely and securely will require technical innovation, strong international cooperation, and public trust. Plutonium truly changed the world, and how we choose to manage it will continue to shape our future for a long, long time.
I've been to places that don't exist yet. I've walked on Mars, explored ancient civilizations that vanished millennia ago, and visited planets orbiting distant stars. Welcome to the Maximus Traveler, where the impossible becomes your next destination. This channel takes you on journeys that break every rule of physics and time. We explore both virtual and real-life travel destinations across Earth and the entire universe. From hidden gems in your backyard to the surface of exoplanets billions of miles away. Whether it's through cutting-edge VR technology or actual space tourism, we're pushing the boundaries of what travel means. Some destinations you can visit today, others you can only experience through simulation, and some don't even exist yet but will blow your mind. Ready to expand your definition of travel? Hit subscribe, drop a comment about where you want to go next, and let's explore the infinite together.